Okay, we're going to finish with one very practical application dual problem here. We have a computer manufacturing company that has two assembly plants, Plant A and Plant B. And so these two ovals I've drawn to represent the two plants. They also have distribution outlets 1 and 2. So the rectangles here represent the distribution outlets. Plant A can assemble at most 700 computers per month, and Plant B can assemble at most 900 computers per month. So what you might want to do is just make a note that Plant A, the maximum they can create is 700, and the maximum Plant B can create is 900. So let's just write that in there. All right, and then Outlet 1 requires at least 500 computers per month. Outlet 2 requires at least 1,000. So let's write in the needs of Outlet 1, which is 500. And let's write in the needs of Outlet 2, which would be 1,000. Okay. Now, the transportation costs for shipping per computer are $6 to ship each computer from Plant A to Outlet 1, $5 to ship each computer from Plant A to Outlet 2, $4 to ship each computer from Plant B to Outlet 1, and $8 to ship the computers from Plant B to Outlet 2. And then it says how many computers must be shipped to each route to satisfy all requirements and minimize the shipping cost. Well, since I need to know how many computers should go along each route, let's let my variables represent the number of computers that are shipped on each route. So X1 will be the number of computers shipped from Plant A to Outlet 1, and you can see I drew X1 going from Plant A to Outlet 1. X2 is the number of computers shipped from Plant A to Outlet 2. So X2 should be, got that one messed up. Let me fix that real quick. That's, if I can, if it'll let me. Alright, that should actually be going all the way over here. Okay, so that should be X2. Right there. So, sorry about that. Okay, so X1 is the number of computers that go from Plant A to Outlet 1. And X2 is the number of computers that go from Plant A to Outlet 2. And then X3 is going to be the number of computers that go from Plant B to Outlet 1. And X4 is going to be the number that go from Plant B to Outlet 2. Okay, now I think we got it right. So just to ignore this little arrow right here. All right, now the first thing I want to do is come up with my objective function. And I know that each of these computers, the ones that go from A to Outlet 1, are going to cost $6 per computer. Each of the ones that go from Plant A to Outlet 2 are going to cost us $5 per computer. Each one that goes from Plant B to Outlet 1 is going to cost us $4 per computer. And each one of these that go from Plant B to Outlet 2 is going to cost us $8 per computer. So putting all that together, I get that my objective function, the cost is going to be $6 times X1 plus $5 times X2 plus $4 times X3 plus $8 times X4. And I wish to minimize that cost function. Now, the assembly constraints, in other words, how many can A assemble? A can only assemble up to 700. So that means that the number of computers that leave Plant A must be less than or equal to 700. And so that would be X1 and X2. So the computers leaving Plant A, X1 plus X2, has to be less than or equal to 700. And then Plant B can assemble no more than 900, so the number of computers leaving Plant B, X3 plus X4, has to be less than or equal to 900. Okay, then we have our demand constraint. Outlet 1 demands at least 500 computers. So 500, look what's coming into Outlet 1. I got X1 computers coming in from plant A and X3 computers coming in from plant B. So X1 plus X3 has to be greater than or equal to 500 to satisfy outlet 1. And then outlet 2, what have I got coming into outlet 2? I've got this X2 over here coming into outlet 2, and I've got this X4 coming into outlet 2. So the number of computers coming from plant A to outlet 2 plus the number of computers coming from plant B to outlet 2, if I add those together, they've got to equal at least $1,000, because 1,000 computers, because outlet 2 has to have at least 1,000 computers. So X2 plus X4 must be greater than or equal to 1,000. So again, you've got your assembly constraints. X1 plus X2 is less than or equal to 700, X3 plus X4 is less than or equal to 900, and you've got your demand constraints for the outlets. X1 plus X3 has to be greater than or equal to 500, X2 plus X4 must be greater than or equal to 1,000. Okay, so now put it all together and we get our linear programming model. And this would be a good problem to have you set up on a test. So anyway, once you set it up, you've got to make sure you got your objective function. You got to make sure you got your problem, these 4 problem constraints, and then you'd have to make sure you have your non-negative constraints. Now, this is a minimization problem, but all the constraints are not going in the same direction. Remember, with minimization, we want the constraints to be all greater than or equal to. But this is minimization, and the first 2 constraints are less than or equal to. The last 2 constraints are okay, but the first 2 are going the wrong way. So what we could do there is we could, if you multiply an inequality by a negative number, remember it reverses the direction of the inequality. So what I could do is I could take those first 2 constraints there and I could multiply those constraints, both of these constraints, by -1. And what that does, obviously it changes all the signs of all the terms, but it also forces the inequality to flip around to greater than. So if I multiply this by -1, that would give me this right here. Negative x1 minus x2 is greater than or equal to -700. And then if I do the same thing to this inequality, it would make that minus x3 minus x4 is greater than or equal to -900. So now I have the model written in standard form, because now it's a minimization problem with all greater than or equal to constraints. And so now I can solve it by the dual method. So if I want to solve it by the dual method, what I would do is I'd write my coefficient matrix. Now I'm going to have a column here for x1, for x2, for x3, and x4, okay? So think about, what are the coefficients here? -1 x1, -1 x2, so -1 here, -1 there, and there's no x3 or x4, and then the constant's -700. Now the second constraint, you have -1 for x3 and -1 for x4. So we'd put the -1s here, and then you have nothing for x1 and nothing for x2, and the constant's -900. The third constraint, you have 1x1, so there's 1x1, no x2, plus 1x3, no x4, equals 500, or greater than or equal to 500. And then your last constraint, you have 0x1, 1x2, 0x3, 1x4 is greater than or equal to 1,000. And then your objective function is just the 6, the 5, the 4, and the 8. So you put the 6, 5, 4, and 8 here, and then you've got 1 right here for 1c. And you know how to transpose it, so if you transpose this matrix, you'll get this matrix. Okay, so now let me get from the transpose, remember, we want to get our dual problem. So our dual problem, remember the bottom row is going to give me my new objective function. So on my dual problem, my new objective function is going to be minus 700y1 minus 900y2 plus 500y3 plus 1000y4, and that would be that function there. And then these rows are going to give me my new less than constraints. But remember, these are y's. So this would be minus y1 plus y3 is less than or equal to 6. This will be minus y1 plus y4 is less than or equal to 5. This will be minus y2 plus y3 is less than or equal to 4. and then this will be minus y2 plus y4 is less than or equal to 8. And so once you write all of those, now you've got your dual problem. Okay, now to solve that dual problem, we have to write our initial system of equations. So we're going to take the first constraint, minus y1 plus y3, and we're going to add the x1 to it to convert it to an equation. Then we're going to take the second constraint, and we're going to add x2 to it to convert it to an equation. Then we'll take this third constraint and add x3 to it to convert it to an equation. Then we'll take this fourth constraint and add x4 to it to convert it to an equation. And then we'll move these four terms to the left of the equal side, and they'll all change signs. So I'll get 700y1 plus 900y2 minus 500y3 minus 1000y4 plus p equals 0. And that's my initial system of equations. And then we can put it in an initial simplex tableau. So you can freeze the video if you need to, and just verify that I put these in the right place. But I'll go over just the first couple of rows. The first equation is minus y1 plus y3 plus x1 equals 6. The second equation is minus y1 plus y4 plus x2 equals 5. And then you can confirm the next two. And the last equation is 700y1 plus 900y2 minus 500y3 minus 1000y4 plus p equals 0. Now, so what do we need to do there? Well, let's go down here and look. We know that this right here, this column right here, has to be the pivot column because negative 100 is the most negative indicator. Now here's something that's interesting. You can't use these zeros because remember, when you pick your pivot rows, you got to use positive numbers, and zeros not positive. So we can only use the one here or the one here. So let's decide which one we're going to use. We need to get our quotient. So if we do 5 divided by 1, we get 5. And if I do 8 divided by 1, I get 8. So that means that 5 being the smaller quotient, that means this will be the pivot row. So I'll pivot on this one. Now, one thing is good about this, having these zeros. Since I have a 0 here and a 0 here, I don't have to do any work to get rid of them. So all I have to do is multiply this row by negative 1 and add it to row 4 to get rid of that 1, and then multiply this row by 1,000 and add it to the fifth row to get rid of the negative 1,000. And I'll let you go through those row operations yourself. But then the next one I'm going to get is going to be this, and so the most negative indicator is actually the negative 500 right here. So I get negative 500, and then again I can't use the zeros, but if 1 divided by 6 is 6, and here 1 divided into 4 is 4, so I've got to pivot on this. So I multiply this row by negative 1 and add it to this to cancel the 1. Then I multiply it by 500, add it to this row to get rid of the negative 500, and then I get to this one. And now on this one, the most negative indicator is actually right here. So negative 300. Well, this one, I can't use the negative 1 because they're not positive. I can't use the 0 because they're not positive. So the only place that I can pivot here is off of this 1. So I'm going to take, so to pivot, I'm going to just take row 4, and add it to row 1 to cancel that negative 1. Then take row 4 and add it to row 2 to cancel that negative 1. Then multiply row 4 by 300 and add it to row 5 to get rid of the negative 300. Finally, I get my final tableau here. And notice at the bottom of the x1 column I have a 0. The bottom of the x2 column I have 700. The bottom of the x3 column I have 500. The bottom of the x4 column I have 300. And p is 7,900. Well, then that means that my solution for the original problem must mean that the minimum cost is 7,900, and I've already given you the values for x1 through x4. So there you have the solution to the problem. From plant A to outlet 1, 0. Plant A to outlet 2, 700. Plant B to outlet 1, 500. plant B to outlet 2 $300 for a minimum cost of $7,900. And there you go. That's it.